Hi, I'm Jessica, and welcome to our second video in the crash course on area and perimeter of plane figures. So you might remember from the first video that we looked at the perimeter and area of triangles, quadrilaterals, regular polygons, decomposable figures, and circles. So in this video, we're going to be looking at arc length of a circle and the area of a circular sector. The video is really more aimed at cycle 1, so secondary 1 or 2 students. Oh, let's go. So in our first example, we have little Leo's bike, which has 2 identical wheels with a radius of 2.2 decimeters. Since Leo is just learning to ride, his bike has small training wheels that are 11 centimeters high. When the front wheel completes 125 revolutions, how many revolutions will each training wheel have completed? Before we get going on this, I have another question for you guys. What type of problem is this? Is it an area problem or a perimeter problem? Definitely perimeter. Okay? This is definitely a perimeter problem, except in this case, because we're dealing in circles here, we use the word circumference to describe perimeter. Same thing. So we're going to have to consider a couple of things when we're working through this problem. One of them is the fact that we have decimeters and centimeters appearing in the same problem. So we're going to have to convert either all to decimeters or all to centimeters. Then we're going to take a look at this and make a little bit of a plan, which I've got right here. Okay, so to tackle the problem, we're going to look at the circumference of the training wheels. Then we're going to look at the circumference of the bike wheels, the total distance, and the number of revolutions made by each training wheel. Before we get started on that, I have a second question for you guys. Which word correctly completes the following statement? Since the training wheel is smaller, it will have to make fewer or more revolutions to cover the same distance as the larger bicycle wheel. You were right if you said more. So we're going to look at that first bit, circumference of the training wheels. And to do that, we're going to calculate the circumference using pi times the diameter. And before we really get going on this, I just want you to imagine that wheel turning, because the circumference, what it's actually doing is that as the wheel turns, imagine it leaving a track. Okay, and after it makes one full revolution, the track that it makes is the distance that the wheel covered, and it is exactly equivalent to the circumference of the tire that made the track. So that's why we're using circumference for our distance here, because it really does tell us exactly how far a tire or the wheel will travel. All right, so in this case, we're going to use pi times diameter because we're given the height of the small training wheels that are 11 centimeters high. That would correspond to the diameter of those little training wheels. So I'm going to leave the 11 centimeters as is, okay, because I want to work in centimeters here. So pi times 11 will give me 11 pi. And if I just stop here, I've left my answer in terms of pi. And that is perfectly acceptable. But if I want to go a little further, then I'm going to take 11 and multiply it by the decimal value of pi to give me approximately 34.56 centimeters. So the circumference here is 34.56 centimeters. All right. Now, if I want the circumference of the bike wheel, I'm going to do the same thing, only this time I'm going to use the variation of the circumference formula that uses radius, because in this case, we're given a radius of 2.2 decimeters. Now, remember I used centimeters in the last calculation, so I'm going to use centimeters again here, which means that I have to take my 2.2 decimeters and convert it to centimeters. And that is where I get my 22. 2.2 decimeters is equivalent to 22 centimeters. Going forward with the calculation, that means I have to take 2, multiply it by pi, and then multiply it by 22. If I want to leave this in terms of pi, that leaves me with 44 pi. Of course, as I did before, if I want to make this, if I want to go a little further, then I can take my 44 and multiply it by the decimal value of pi to give me approximately 138.23 centimeters. Okay, so now we're going to use these numbers to figure out the total distance. And the total distance, I'm going to show you 2 ways to do it. The first way is using all numbers, and the second way we're going to use it in terms of pi. So the total distance is equal to the circumference times the number of revolutions. So in this case, we're going to take the 138.23 centimeters per revolution and multiply that by the 125 revolutions that the problem said the front wheel makes. That will give us 17,278.75 centimeters, if I wanted to convert this to meters, that corresponds to 172.79 meters. In terms of pi, what happens here then is that my total distance is still going to be calculated using the circumference times the number of revolutions, but this time I'm going to use the 44 pi centimeters per revolution and multiply that by the 125 revolutions that the problem gave me. And that gives me 5,500 pi centimeters. So in terms of pi is a little more precise than when I convert it into the decimal values, but either way is fine. So then to go on with this, finishing off the problem here, I need to know the number of revolutions made by each training wheel. So to do that, again, I'm going to look at it two ways. The number of revolutions is equal to the distance traveled divided by the circumference. So the first way, of course, uses the numbers. So 17,278.75 centimeters divided by 34.56 centimeters per revolution is going to give me approximately 499.96 revolutions. If I do the same calculation, this time using in terms of pi, that means that I'm going to have 5,500 pi centimeters, which I'm going to divide by 11 pi centimeters per revolution to give me 500 revolutions. And you might wonder what happened to pi, but of course, if I divide pi by pi, in other words, if pi is in the numerator and pi is in the denominator, then pi cancels out and I'm left with 500 revolutions, which is, again, more precise than the above method, but either way is totally acceptable. So in our second example, we've got an automatic sprinkler. It's installed on a lawn. The water jet can reach a maximum distance of 15 meters. The angle of rotation is set to 260 degrees. And we're wondering what is the area of the lawn that can be watered. So I'm going to just put up a little diagram of this right here to get a good visual of what's going on. So you can see the entire circle that if I had set my sprinkler to 360 degrees, this is how much it would be watering. But I don't want it set to 360 degrees. I want it set to 260. So you can see that the dark green zone, that is what I am watering according to the setting that I've decided on. And the distance that my jet will reach is shown there by that 15 meters, which corresponds to the radius of the circle. So the first thing we're going to do here is get the area of the entire circle, because I just need to figure out how much of that is that big green zone there, which we call a circular sector. Okay, so the area of the entire circle is found by taking pi and multiplying it by the radius squared. So pi times the radius squared gives us pi times 15 squared, which, if I want to leave it in terms of pi, gives us 225 pi. Of course, if I multiply 225 by the decimal value of pi, that's going to give me approximately 706.86 meters squared. So this represents the entire circle's area. To be able to find the circular sector, which is the dark green zone, actually technically the light green zone is also a circular sector, but the one I really want is the dark green one. So that's the one I'm going to use in my calculation, all the information about that one. So the relationship that exists between the circular sector and the entire circle is shown to us here. If we take the central angle, which in this case for us, it's 260 degrees, and we put it over the 360 degrees, which represents the degrees of the entire circle, and set that equal to the area of our circular sector, which is the area of the dark green that we're interested in, over the area of the entire circle, which of course we calculated up here, then we'll be able to figure out the area that we're interested in. I've included down here, though, the relationship that exists between the length of the arc of a circle, because it's in the circumference of the circle, because it's actually kind of the same relationship. And it's interesting to note, since we're already talking about perimeter too. So we won't need that one for our calculation this time, but you might need it in the future. So if we look at the same circular sector, which is created by that 260 degrees, and of course I've colored it in dark green, the edge of that, okay, the distance around just that sector along the outside of the circle there is what we call the arc for that circular sector. So I can use the degrees, that 260 degrees over 360, and I can figure out the length of that arc, the distance, from one side of that dark green zone to the other side of the dark green zone, by putting it over the circumference of that entire circle. Right? So it's kind of cool. But we're going to go back to our circular sector because that's the one we need for this problem. This is clearly an area problem. So central angle was 260 in this case. So I'm going to put that over 360 degrees. And I'm going to set that equal to the area of the circular sector or area of the sector. That's what we're looking for. So I'm going to leave that blank. I don't know it yet. And I'm going to put it over the entire area of the circle, which is 706.86 meters squared. And I calculated that up here. Isolating the area of the sector will give me 706.86 multiplied by 260 degrees divided by 360 degrees to give me 510.51 meters squared. And that 510 meters squared is the area of the lawn that will be watered. So when I finish this off properly, I just write a little sentence here. The area of the lawn that will be watered is 510.51 meters squared. And that's it. We're done. So that brings us to the end of our second video on perimeter and area of plane figures. If you missed the first one, I'd encourage you to go and check that out. And if you're looking to get a deeper understanding or just practice some of the skills, then I'd encourage you to go and check out some of the exercises that are associated to these videos. Until next time, I'll see you guys later. Bye.